Let's say that I have the complex number z, and in rectangular form, we can write it as -3 plus -3 plus 2i. So first, let's think about where this is on the complex plane. So this is our imaginary axis, and that is our real axis, And let's see, the real part is -3. So we could go 1, 2, 3 to the left of the origin. Let me space that out a little bit more evenly. So 1, 2, 3 to the left of the origin. So -3. And then we have 2i. So we're going to go up 2. So up 2 in the imaginary direction. So 1, 2, just like that. And so z is real part -3, imaginary part 2. Z would be right over here in the complex plane. So that is z right over there. Now what I want to think about are other ways to essentially specify the location of z. And in particular, instead of giving the real and imaginary parts, essentially the coordinates here, let's think about giving a direction and a distance to get to z. So for example, we could give the distance from the origin to z. So let's call this distance r. But that distance by itself isn't enough to say where z is. You have to say, in what direction do you have to go a distance of r to get to z? And so to specify the direction, we will have this angle theta in radians, this angle between the positive real axis and this line right over here, this line or the segment that connects the origin and z. So if someone gave you this angle and this distance, then you could get to z. Now what I want you to do right now is pause this video and see if you can find a relationship between r theta and -3 and 2. In fact, given this complex number in rectangular form, can you figure out what r and theta are? Well, let's think through this a little bit. And to help us that, let's remind ourselves of the unit circle definition of trig functions, because we are going to use some trig functions to relate r theta and 2 and -3. So I'm going to construct a unit circle here. So construct a unit circle. So this right here is a unit circle, circle of radius 1. So construct a unit circle. That's a unit circle. So by definition, what are the horizontal and vertical coordinates of this point right over here, where this line intersects the unit circle? Well, this is forming an angle of theta with the positive real axis. And so the horizontal coordinate over here, by definition, is going to be cosine of theta. Cosine of theta. That's the unit circle definition of cosine of theta. And the vertical coordinate is going to be sine of theta. Sine of theta. And so what would the horizontal and vertical coordinates of this point be? We obviously know they're -3 and they're 2, but what would they be in terms of cosine theta and sine of theta? Well, look, this point right over here is a radius of 1 away from the origin. So this distance right over here, that distance right over here is 1. But now we are r away from the origin, where r times as far. So for r times as far in that direction, then we're going to be r times as far in the vertical direction and r times as far in the horizontal direction. We're going to have to scale we're going to scale everything by r. So the horizontal coordinate of this point right over here, instead of it being cosine of theta, it's going to be r times cosine of theta. So this point right over here, which we know is -3, is going to be equal to r cosine of theta. And by the same logic, this point over here, the vertical coordinate, we're going to scale up sine theta by r, where r times is far. So this point right over here is going to be r sine theta. And we already know that that's equal to 2. R sine theta. So given that, can we now figure out what r and theta are? So let's first think about figuring out what theta is. So to do that, let's think about our trig functions. So one trig function that involves sine theta and cosine theta is tangent theta. So for example, we could say tangent theta, tangent of our angle, tangent of theta is equal to sine of theta over cosine of theta But we could also multiply the numerator and denominator here by r. That won't change the value. So that's the same thing as r sine theta over r cosine of theta. And we know r sine theta is going to be equal to 2. And we know that r cosine of theta is negative 3. So this whole thing is going to be negative 2/3. Another way of thinking about it is the tangent of tangent of theta is going to be the same thing as the slope of this line right over here. And what's the slope of that line? Well, if you start at z and you want to go to the origin, you're going to go positive 3 in the x direction, and then you're going to go negative 2, or as you could say positive 3 in the horizontal direction, and then you go negative 2 in the vertical direction. So the slope is your change in vertical over change in horizontal. It's negative 2 over 3. Negative 2 over 3. But now we can use this to solve for theta. To solve for theta, we just take the inverse tangent of both sides. And we get theta is equal to inverse tangent of negative 2/3 of this thing right over here. So let me copy and paste that. And we could get our calculator out to figure out what this actually is. So let's turn it on. Let me make sure that I am in radian mode. I am. And so I can take the inverse tangent of negative 2 divided by 3, which gets us negative 0.58800, on and on and on. So if we round to the nearest hundredth of a radian, it'd be negative 0.59. So this is approximately negative 0.59. Now, is this the right angle? Is this the theta? Is this the theta that we are looking for? Well, this theta, negative 0.59, that's going to get us over here. That's this angle right over here. That's what the inverse tangent gave us. And it makes sense because this ray is a continuation of this ray right over here. Together they would form a line. It has the same slope. But that's not the theta that we are looking for. The theta that we are looking for is going in the opposite direction. It's halfway around the circle. So if we think in terms of radians, it's going to be this angle plus pi radians. So the theta that we're looking for isn't 0. It isn't going to be what our calculator gives us for this. It's going to be this value plus pi. So theta, the theta that we care about, is going to be negative 0.59 roughly plus pi. Let me say approximately, just because I have rounded right over here. So let's get the calculator out. So let's take our previous response, and that's just the previous answer, plus pi, because we're going to go in the opposite direction. So that gives us roughly 2.55 radians. So this is approximately 2.55 radians is our claim for what theta is. Now, does that make sense that this angle right over here is 2.55 radians? Well, this angle, if we go straight up, that's pi over 2 radians, and pi is 3.14, so that's going to be 1.57, right? 1 point something like that. And this is pi radians, so that's 3.14. 159, keep going on and on and on. So 2.55 is indeed in the right quadrant. So that is right. This is going to be an angle of 2.55 radians. Now we just have to figure out the length, what r is. And that we can just use the Pythagorean theorem for. We could set up a right triangle. We know that this distance right over here is 2, because this distance right over here is 2. And we know that this distance is, the coordinate here is negative 3, but the distance here is just 3. So we know from the Pythagorean theorem that r squared is equal to 2 squared, plus 3 squared, or that r is equal to the square root of 4 plus 9, which is 13. And so there we have it. We have negative 3. So we know r is equal to square root of 13, and theta is 2.55 radians. So using that information, we can now rewrite z in terms of r and our theta. So now we can say that z is equal to, instead of negative 3, we can write it as r cosine theta. So we can rewrite it as square root of 13 times the cosine of theta, which is, we're saying theta is roughly 2.55 if we round to the nearest hundredths, plus 2, we already know, is r sine of theta. So r is square root of 13, and then sine of theta, 2.55. And then all of this we could say, or all of this is going to be multiplied times I. And if we like to simplify it a little bit, or to kind of really make clear what the r is here, we could factor it out. So we could say that z is equal to square root of 13 times cosine of 2.55. And once again, 2.55 is an approximation, so maybe I should say approximately equal to cosine of 2.55 plus, I'll throw the I in front, plus I times sine of 2.55. And so when I rewrote z in this format right over here, it makes it much clearer what the direction I have to go in is. The direction is 2.55 radians counterclockwise from the positive real axis. And it also says how far I need to go. I need to go square root of 13. So this essentially makes the polar, it makes it clearer how we get there in kind of a more, I guess you could say, polar mindset. And that's why this form of the complex number, writing it this way, is called rectangular form, while writing it this way is called polar form.